Welcome to today's class. In today's class, we discuss about the topic that is non-linear programming. The main objective of this non-linear programming is to learn about the concept of non-linear programming, the difference between LPP and NLP, and what is actually quadratic programming, what is separable programming. These are the topics we discuss in today's class. Now, what is actually non-linear programming? As we know, LPP in linear programming problem, there are different equations. The first equation is the objective function, and then the second equations are the constants, subject to constants, and the third equations are the conditionality equations. In conditional equations, all the variables, decision variables must be greater than equal to 0, means all the values are positive. In constant, the equations may be equal or inequality. Either it is less than equal to or greater than equal. And the objective function consists the decision variables of degree 1. So that's why these are the linear equations. In linear equation, all the variables must have the degree 1. But when the degree of the variables are more than 1, it becomes non-linear equation. In mathematics, we know that 2x plus y equal to 5. So there are two variables, x and y, and the degree of the variable of x is 1 and the degree of the variable y equal to 1. If you plot the points by using a graph paper, it becomes a straight line. So it is a linear equation. And we solve this linear equation by using the LPP problem. That is, there is a objective function and number of constant equations are there, and the condition is that all the variables must be positive. Means you draw the graph, you find the visible region in the positive quadrant, that is in the first quadrant. But here the term nonlinear programming usually refers to the problem in which the objective function becomes nonlinear. Nonlinear means what? The degree of the variable must be greater than 1. Let us consider one example. The objective function is written like that: z equal max, max or mean. Max or mean, z equal to x1 square plus x2 square. Here x1, the degree is 2, and for x2, the degree is 2. Then it is a nonlinear equation. Or it may be written as x1 plus x2 square. Here also, the degree of the x2 is more than 1. It is a nonlinear equation. Nonlinear or one or more of the constant inequalities have nonlinear relationship. Means the constant equations may also be the nonlinear relationship or both. In actual practice, such situation occurs if a purely linear relationship may not exist in the profit or cost function when the production levels are varying. For example, production cost and revenue vary non-linearly with the scale of the operations. Means it is not a straight line. If you draw the points, you take the points, and if you draw by using a graph paper, sometimes it is not a straight line, it's just like a curve. The general optimization problem is to select n decision variables, that is x1, x2, x3 in this way up to xn from a given feasible region in such a way as to optimize. Optimize means what? Minimization or maximization. Maximize the profit and minimize the cost. A given objective function f of x1, x2 up to xn of the decision variables. The problem is called a nonlinear programming problem. In the short way, it is written as NLP. NLP means actually non-linear programming. If the objective function is non-linear and or the feasible region is determined by non-linear constraints, thus in maximization form, the general non-linear program is stated as, it is a general form, mathematical representation of the NLP. That is, maximize function of x1, x2 up to xn subject to g1 of x1, x2 up to xn less than or equal to b1. That means it is the inequality equation. Similarly, g of m x1, x2, up to xn less than or equal to bm. These are the subject to constant equations, where each of the constant functions g1 through gm is given. A special case is the linear program that has been treated previously. The obvious occasion for this case is function of x1, x2 up to xn equal to, we can write in this way, the summation j equal to 1 to n c of j and x of j, and gi of x1, x2 up to xn equal to summation aij into xj, where I equal to 1 to m. Note that non-negativity restrictions on variables can be included simply by appending the additional constants. Then, the example of nonlinear programming. Let us consider an investor has $5,000 and two potential investments. Let xj for j equal to 1 and j equal to 2 denotes his allocation to invest j in thousands of dollars. From historical data, investments 1 and 2 have an expected annual return of 20% and 16%, 20% and 16% respectively. Also, the total risk involved with investment 1 and 2 as measured by the variance of total return is given by the equation, that is 2x1 square plus x2 square into x1 plus x2 whole square, so that the risk increases with total investment and with the amount of each individual investment. The investor would like to maximize his expected return and at the same time minimize his risk. Clearly, both of these objectives cannot in general be satisfied simultaneously. There are several possible approaches. For example, he can minimize the risk subject to a constant or imposing a lower bound on expected return. Alternatively, expected return and risk can be combined in an objective function to give the model. So this is one example here, the portfolio selection. Then again, I am converted, that means how to formulate the NLP of this example. Maximize function of x, that is z, equal to 20x1 plus 16x2 minus theta of 2x1 square plus x2 square plus x1 plus x2 whole square. This is known as the function of fx, or you may represent as z. What are the subject to constant? The subject to constant is g1x equal to x1 plus x2 less than or equal to 5. And the conditional equations are x1 must be positive and x2 must be positive. That's why it is mentioned as x1 greater than or equal to 0, x2 greater than or equal to 0. That is g of 2 of x equal to minus x1 and g3 of x equal to minus x2. The non-negative constant theta reflects its trade-off between risk and return. Now, we discuss if theta equal to 0, the model is a linear program. If you put theta value in the equation, maximize f of x equal to 20x1 plus 16x2 minus theta into 2x1 square plus x2 square plus x1 plus x2 whole square. If we put theta value 0, then what is the objective function? Maximize f of x equal to 20x1 plus 16x2. Here, the degree of x1 is 1 and degree of x2 is 1. Hence, it is a linear equation. So that's why I'm writing here, if theta is 0, the model is a linear program. And by using the graphical method or by using the simplest method, we can solve it. But the investor will invest completely in the investment with the greatest expected return. That's why for very large theta, the objective contribution due to expected return becomes negligible. And the investor is essentially minimizing the risk. This is actually one example of the portfolio selection. Another example, sales revenue. Let us consider in marketing, we usually observe that the lower a product price, the greater the sales quantity. It is general, it is a tendency. If you less the product price, automatically the sales will increase. That's why I'm writing here, in marketing, we usually observe that lower a product price, greater the sales quantity. The sales quantity will be increased because more customer will purchase that item, that product. Therefore, sales revenue does not vary proportionality with price. Consequently, this phenomenon reflects the objective function to be linear because it is a straight line. For example, let S of P means sales of product represents the sales quantity as a function of the price P. Then P, SP is associated sales revenue. If the sales quantity function is linear, say S of P equal to AP plus B over the range of interest for P, then the sales revenue component in the objective function is quadratic. A of P square plus B of BP, where P is known as decision variable. This is another example of sales revenue. One more example on nonlinear programming is safety stock inventory level. Safety stock are usually maintained to accommodate weekly fluctuations in sales. One approach is used to solve such a multi-period model is to let the safety stock level for an item be a function of both its forecasted sales quantity and the fraction of capacity utilization, which implies by this forecast. Let us consider an example here. Let C be the weekly capacity available to produce an item. S, the item's forecasted average weekly sales, where C be the weekly capacity available to produce an item or any product. S, the item's forecasted average weekly sales, and NS, the item's safety stock level, where N denoted as the number of weeks sales depending on the capacity utilization factor. To explain this, suppose management has established the formula for N to be N equal to M plus f of s slash c. Then the resultant safety stock label is a quadratic function. ms plus f slash c into s square of the item's forecasted average weekly sales. Such label may appear in many of the planning model constants as well as in the objective function. This is another example of safety stock inventory labels of NLP. Now, as we already discussed, LPP is a linear programming problem where there are three types of equation. One is your objective function, it may be maximize or minimize. We can represent that is Z, summation I equal to 1 to n xi. So, here we may also write the nonlinear programming problem mathematically, that is measure max or mean Z equal to C of x1, x2 up to xn. That means Cx1 plus Cx2 plus Cx3, in this way Cxn. Subject to constraints a1 of x1, x2 up to xn equal to b1 or less than equal to b1 or greater than equal to b1. In LPP, that is inequality, less than equal to or greater than equal to. Here, in nonlinear programming problem, the constant equations may consist equal to, less than equal to, or greater than equal to. Similarly, all the constant equation mentioned in this way, a2 of x1, x2 up to xn less than equal to b2 or equal to b2 or greater than equal to b2. In general, if there are m constant equations, a of m of x1, x2 up to xn less than equal to or greater than equal to or equal to bm, and all the decision variables, that is xj greater than equal to 0. That means positive. Where either c of x1, x2 up to xn or sum of the constant equations a of I x1, x2 up to xn either less than equal to or greater than equal to or equal to or both are non-linear. In matrix notation, the general nonlinear programming problem may be written as follows. Max or mean z equal to c of x. Earlier I am writing there z equal to c of x1, x2, xn. In this way you may also define max or mean z equal to c of x subject to constant ai of x less than equal to, greater than equal to or equal to bi, where I equal to 1, 2, 3 up to m, and x is always positive, that is mentioned as your x greater than equal to 0, where either c of x means objective function or sum of the constant functions or both are non-linear in x, means the decision variables must have degree more than 1. Then there are different other concepts in nonlinear programming, that is quadratic programming. What is actually quadratic programming? Quadratic programming, QP, is the process of solving certain mathematical optimization problem. Optimization problem is either maximization or minimization involving quadratic function. In quadratic function is what? The degree is 2. Specifically, one seeks to optimize, that is minimize or maximize, a multivariate quadratic function subject to linear constants on the variables. So quadratic programming is a type of nonlinear programming. Programming in this context refers to a formal procedure for solving mathematical problems. Quadratic programming formulation process. The quadratic programming problem with n variables and m constant. Let us consider there are n variables x1, x2, x3 up to xn and m constants, that is a1 of x, a2 of x, a3 of x up to am of x can be formulated as follows. Given a real valued n-dimensional vector C and n into n dimensional real symmetric matrix Q and m into n dimensional real matrix A and an m-dimensional real vector B. The objective of quadratic programming is to find an n-dimensional vector x that will minimize the objective function with respect to the subject to constraint. That means minimize half of xt into qx plus c of t x and subject to ax less than equal to b, where xt denotes the vector transpose of x. I mentioned here capital T, that is not the xt denotes the vector transpose of x, and the notation ax less than equal to b means that every entry of the vector ax is less than or equal to the corresponding entry of the vector b, component wise inequality. Then another concept in NLP is separable programming. Separable programming is an approximate method of solving certain nonlinear programming problem. A separable function is one which can be expressed as the sum of subfunctions where each subfunction is a function of one variable only. I have explained with an example, that is f of x1, x2, x3, that is the objective function, equal to 4x1 square plus 7x2 minus 3 whole square plus 11e to the power x3. That is f1 x1 plus f2 x2 f3 x3, where f of 1 x1 equal to 4x1 square, f of 2 and function 2 and of x2 equal to 7 into x2 minus 3 whole square from the objective function. What is f3 x3? That is 11 e to the power x3. The separable programming method is applicable if the objective function and the various constants are separable. The general form of a separable programming problem is given by, we can represent the separable program mathematically as follows. Maximize FO x1, x2 up to xn subject to constant f of I x1, x2 up to xn less than equal to bi, where I equal to 1 to n, and xj greater than equal to 0, j equal to 1 to n. If the objective function and the constants are separable, then we can write f0 x1, x2 up to xn equal to summation j equal to 1 up to n f0j of xj. Similarly, f of I in general, f of I of x1, x2 up to xn equal to summation j equal to 1 to n f of ij of xj, where I equal to 1 to m. Thus, the problem under consideration can be expressed as maximize summation z equal to 1 to n f0j of xj subject to summation z equal to 1 to n fij of xj less than equal to bi, where I equal to 1 to m. That is the mathematical representation of the separable programming. And this is the graph here. It is not linear. Then, graphical method to solve NLP. So before we discuss about the graphical method to solve the non-linear programming, again I am discuss what is actually the linear programming. As we know, linear programming problem consists a objective function of degree 1 and number of constant equations must have degree 1 with inequalities either less than equal to or greater than equal to, and the condition equation, that is the decision variables, greater than equal to 0, always positive value. And as we know, you can solve data LPP by using graphical method or simplex method. In graphical method, we draw the straight lines, and the first job is we have to find the feasible region. After finding the feasible region, we collect the corner points, and by taking the corner points, we put that value of that points in the objective function. And as per the question, if it is maximized, we have to find the maximum z, where the max z value is maximum, that is our optimal solution. If it is mentioned as minimum, then we have to find where the z value is minimum, and we get the optimal solution. So, linear programming problem is characterized by the presence of linear constants and linear objective functions in decision variable. There are, however, problems in real life situations where neither the objective function nor the constants are linear functions in decision variable. Let us consider one example. Suppose 40 cubic meters of a granular product are to be transported across a river. Any amount of the product can be transported in one trip, and regardless of how much is transported at one time, the cost is rupees 10 per trip. That is a 10 rupees per trip. The cost per square meter for the sides, bottom and end of a container are as follows. Ends rupees 20 square meter, bottom rupees 10 per square meter, sides rupees 10 per square meter. If a very small container is used, the container cost will be low, but many trips will be necessary and transport cost will be excessive. If you decrease the size of the container, then many number of trips is required to shifting your product from one side to another side. But many trips will be necessary and transported cost will be excessive. If a large container is constructed, the transport cost will be low. If the container size is bigger, automatically the transport cost will be low. There is a restriction that maximum number of trips is 30. This problem can be formulated as nonlinear programming problem. Solution of a nonlinear programming problem. The method of solving a linear programming problem is based on the property that the optimal solution is located at one or more extreme points of the solution space. T is the property enables us to limit our search to corner points of the feasible region and thus to obtain the optimal solution in a finite number of iterations. Unfortunately, no such universality regarding the nature of optimal solution can be established in nonlinear programming model. In nonlinear programming problem, the optimal solution can be located at any point along the boundaries of the feasible region, or it can even be located within the feasible region. Means the point, the optimal solution point may be on the boundary or inside the feasible region. Secondly, due to non-linearity of the objective function and the constraint, it can be difficult in certain cases to distinguish between the local and the global solution. In addition, it is sometimes difficult to test optimality of the nonlinear programming problem. The problem is especially difficult when feasible region is non-cave, non-convex type. So this is actually the solution procedure. And what is actually a concave and convex function? Let us consider a function f of x, or a objective function I mention as f of x1, x2 up to xn. A function f of x1, x2 up to xn equal to f of x is said to be convex over a convex set S when the shape of the function is such that for any 2 points x and y in S, the line joining f of x and f of y must be above the function. Must be above the function. Similarly, for concave, the shape of the function is such that for any 2 points x and y in S, the line joining f of x and f of y must be below the function. Then the characteristics of convex and concave functions by partial derivatives. So what happens? If the function is f of x1, x2, up to xn, we have to calculate the partial derivatives. That is the second order partial derivatives. So you have to first find if you derivative a function with respect to x, that is known as d of f of x divided by dx. If you derivative again with respect to x, that is d square f of x divided by d of x square. Hence, if I am represent, it becomes h of x equal to del square f divided by dx1 and del x2. When h of x is positive, it is convex. If it is negative, it is positive, it is concave. If it is negative, that is convex. Then we try to solve the nonlinear programming by using graphical method. One of the solving method of nonlinear programming problem is graphical method, which is also called as geometrical method. The graphical method is the easiest method for solving nonlinear programming problem. It is defined on well-defined sets of logical steps. In NLPP, that is nonlinear programming problem, which contain two variables, can be easily solved by graphical method. As we can observe that from the characteristics of the curve, we can achieve more information, and from this information we can obtain the optimal solution of the given problem. But in the case of NLP problem, the optimum solution or may not be the occur at one of the extreme points of the solution space. It generated by the constants and the objective function of the given problem. Now, some steps we follow to solve the graphical method, to solve the non-linear programming by using graphical method. The following steps are used in the graphical solution of the non-linear problems, and we will apply these steps in some examples. The first step is formulate. That means read the question and you write the NLP problem in standard form, that means mathematical form, which have the objective function and constant set. In this step, second step, in this step, we construct the graphs and plot a constant curve where the constant curve represent the limitation of the available resources. Because in a linear programming problem, whenever you use graph by graphical method, by using graph paper, we can solve it. So we draw the straight lines. Suppose x1 plus x2 less than equal to 5. If I am putting x2 value 0, you get x1, that is one point is 5, 0. If we put x1 equal to 0, another point we get, that is 0, 5. So by taking these 2 points and plotting on a graph, we get a straight line in the first quadrant of the graph paper. Similarly, in the nonlinear programming problem, we also plot the points on the graph paper and draw the graphs. So the graphs may be linear or curve like that, because nonlinear programming problem having more than degree 1 means it is nonlinear equation. So definitely we may get a hyperbola, we may get a parabola, we may develop a curve, we may develop a circle, we may develop a concave safe graph or concave safe graph like that. So in second step, in this step, we construct the graph and plot the constant curve, where the constant curve represents the limitation of the available resources. Then third step is identify the convex region of the solution space generated by the objective function and constants of the given problem. Then the fourth step is determine the point in the convex region in which the optimum solution always occurs. That is the fourth step. Determine the point in the convex region in which the optimum solution always occurs, and the most attractive corner is the last point in the feasible region. Determine the optimal solution by mathematically calculating coordinates of the most attractive points. The last step is, for the optimal solution of the problem, we must determine the value of the objective function. Let us consider one example. I am writing here. Solve the following nonlinear programming problem graphically. And the objective function is max z equal to 2x1 plus 3x2. Subject to constraints, that is, subject to constant, that is x1 dot x2 less than equal to 8. Here, the degree of x, the variables, is 1, 1. But in the second constant equations, it is x1 square plus x2 square less than equal to 20. That means the degree is more than 1. It becomes 2. That's why it is a nonlinear constant equations. And x1, x2 equal to 0. Clearly, the feasible region will lie in the first quadrant only because x1 greater than equal to 0 and x2 greater than equal to 0. Now we plot the curve of the given constant x1 square plus x2 square equal to 20. That means the one constant is there, x1 square plus x2 square equal to 20 and xy equal to 8. It is given in the question. As you know, the equation of a circle is x1 square or x square plus y square equal to r square. A square plus y square equal to r square. Here, the 2 points are x1 square plus x2 square equal to 20. x1 is one axis, another value is you can put on the x2 axis. That is x1 square plus x2 square equal to 20. Represents a circle of radius root over 20 with center of the origin, and x1 dot x2 equal to 8. Represents a rectangular hyperbola whose asymptotes are the coordinate axis. Asymptotes are the coordinate axis. Solving the equation x1 square plus x2 square equal to 20 and xy equal to 8, since we know x1 plus x2 whole square, that means a plus b whole square. What is the actually value? A plus b whole square is a square plus b square plus 2ab. By using that formula here, x1 plus x2 whole square equal to x1 square, that is a square, plus x2 square, that is b square, plus 2ab, that is 2x1 into x2. Then x1 plus x2 whole square equal to, if I am putting the value of x1 square plus x2 square is 20 and xy is 8, in this equation we get 20 plus 2 into 8, that is 36. That is 8 into 2, that is 16, plus 20, that is 36. Similarly, x1 minus x2 whole square. So a minus b whole square, the formula is a square plus b square minus 2ab. So now we put that formula here, x1 minus x2 whole square, that is x1 square plus x2 square minus 2x1 into x2. Then x1 minus x2 square equal to 20 minus 2 of 8 equal to 4. That is 8 into 2, that's 16, 20 minus 16, that is 4. Adding the two equations, equation 1 and equation 2, we get x1 equal to 4 and x2 equal to 2. That is, we get the value of x1 and x2. Thus, the intersection coordinates of these two curves are b of 4, 2 and d of 2, 4, lying in the first quadrant, shaded by the horizontal lines, satisfy the constants x1 square plus x2 square less than equal to 20. Whereas x1 greater than equal to 0, x2 greater than equal to 0, where the points x1 and x2 lying in the area shaded by the vertical line satisfy the constant x1 dot x2 equal to 8 and x1 greater than equal to 0 and x2 greater than equal to 0. Thus, the desired solution point x1, x2 may be somewhere in the non-convex feasible region. Non-convex means the points O, A, B, C, D, E, shaded by the both horizontal and vertical lines. The required point is obtained by moving parallel to the objective line. What is the objective function here? I am mentioning 2x1 plus 3x2 equal to c for some constant z equals c. We go on moving parallel to the objective line. 2x1 plus 3x2 equal to 6. Away from the origin, so long as the line c equal to 2x1 plus 3x2 touches the extreme boundary of the feasible region. In this problem, the boundary point 2, 4 gives the maximum value of the z. That is the objective function. And this is the graphical figure of this above example. And the graphical solution of the problem finally obtained as x1 equal to 2, x2 equal to 4, and max z equal to 16. So This is the graph here. This is the circle. X square plus y square is 20. You have to find the radius and draw the straight line. Draw the curve. Then draw the other points as per the constants and find the 2 points here. Then solving the equation x1 square plus x2 square equal 20 and xy equal to 8, since we know x1 plus s square equal to 36 and x1 minus x2 whole square equal to 4. So from the graphical solution, the problem finally obtained as x1 equal to 2 and x2 equal to 4. That is the point. 2 points are there on the first quadrant, that is one is your D and another is your B. So x1 is 2 and x2 equal to 4 is the max z equal to 16. We get that. That's the solution process. Similarly, I have explained one more example of the graphical method. Solve the following NLP problem graphically. The question gives max z equal to 8x1 minus x1 square plus 8x2 minus x2 whole square. Subject to constant, two constant equations are given here. x1 plus x2 less than or equal to 12, x1 minus x2 greater than or equal to 4. Inequalities are there, and x1 x2 greater than or equal to 0. So this is actually the question. Then the solution. Let OX1 and OX2 be the set of rectangular Cartesian coordinate axes in the plane paper. Since x1 greater than or equal to 0 and x2 greater than or equal to 0, the feasible region will lie in the first quadrant only. And this is the figure actually. The feasible region is shown by the shaded region in the figure that I am mentioned in the graph. The gradient of the tangent to this circle can be obtained by differentiating the equation. What is the objective function? You represent as z equal to 8x1 minus x1 square plus 8x2 that minus x2 square, that is given in the question. So if we differentiate with respect to x1, that means x2 is constant. Then what do we get here? With respect to x1, we get 8 minus 2x1 plus 8 dx2 divided by dx1 minus 2x2 into dx2 dx1 equal to 0. Because we derivative the equation objective equation both sides. Or dx2 divided by dx1 equal to 2x1 minus 8 or 8 minus 2x2. That is, from this equation after derivative with respect to x1, we grouped the common variables, that is 8 minus 2x1 and minus 2x2 dx2 divided by dx1 and 2x1. If we taking the common, we get here dx2 divided by dx1 equal to 2x1 minus 8 divided by 8 minus 2x2. The gradient of the line x1 plus x2 equal to 12 and x1 minus x2 equal to 4 is dx1 plus dx2 equal to 0 or dx2 divided by dx1 equal to minus 1 and dx1 plus dx2 equal to 0 or dx2 divided by dx1 equal to 1 means the derivative of x2 with respect to x1 equal to 1 or positive 1 or negative 1. If the line x1 plus x2 equal to 12 is the tangent to the circle, that's mentioned here. x1 plus x2 is the tangent to the circle. Then the substituting d of x2 with respect to x1 equal to minus 1 and 2 of x1 minus 8 divided by 8 minus 2x2 equal to minus 1. By solving it, we get that by cross multiplication 2x1 minus 8 equal to minus 1 into 8 minus 2x2. If I'm open the bracket, 2x1 minus 8 equal to minus 8 plus 2x2, that is 2x1 equal to 2x2, x1 equal to x2. And here we find that x1 equal to x2, the equation x1 plus x2 equal to 12 gives x1, x2, the points are 6, 6. This means that the tangent of the line x1 plus x2 equal to 12 is at the point 6, 6. Similarly, if the line x1 minus x2 equal to 4 is the tangent to the circle, then substituting d of x2 with respect to x1 equal to 1 from the equation 2x1 minus 8 divided by 8 to minus 2x2 equal to 1 by cross multiplication and open the bracket, we get 2x1 minus 8 equal to 8 minus 2x2. Again, 2x1 plus 2x2 equals 16, so x1 plus x2 equal to 8. Adding the equation x1 plus x2 equal to 8 and x1 minus x2 equal to 4, we have the 2 points, that is x1 and x2 becomes 6, 2. This means that the tangent of the circle to the line x1 minus x2 equal to 4 is at point 6, 2. This point lies in the feasible region and satisfied with the constants. Thus, the optimal solution is x1 equal to 6 and x2 equal to 2, where z is 24. That is I mentioned in the graph. So AC is the line that is tangent to the circle. x1 plus x2 equal to 12. Similarly, another line is x1 minus x2 equal to 4, tangent to the circle, and we get the feasible region, and you have to find where the z is maximum. Then Tucker condition. What is actually the Tucker condition? It's a very important part of the non-linear programming problem. The optimum solution of a general non-linear programming problem can be identified by using a set of conditions developed by Tucker. These conditions are as follows. Let us define m plus 1 general functions of n variables, that is x1, x2 up to xn as f, and g1, g2 up to gm. The general nonlinear programming is maximize, it can be formulated as maximize the objective function h f of x1, x2 up to xn subject to constant, that is the g of I x1, x2 up to xn less than equal to bi. What is I? I equal to the index, that is I equal to 1 to M. The set of constants also include the non-negativity constants. A set of necessary but not sufficient conditions for the optimal nonlinear programming, that is lambda I g of I x star equal to 0, where I equal to 1 to m. So that is the Kontaker conditions. If the objective function is concave or maximization or convex for minimization and the feasible region is convex, Kontaker conditions are necessary and sufficient. So after solving the nonlinear programming, it is required to check by using the Kontaker conditions is satisfied or not. The quality programming is also applicable in portfolio selections. Now, we summarized of the today's class. So what is nonlinear programming and how it is different from the linear programming problem? So linear programming problem, all the decision variables having degree 1, but in nonlinear programming, the decision variables may have the degree more than 1, or the constant equations are less than equal to or greater than equal to. That is the difference between LPP and NLP. And how to formulate the mathematically the nonlinear programming and subject to constants, and the examples of the portfolio selection and the examples of sales revenue and the example of safety stock inventory levels and the mathematical representation of the general nonlinear programming problem. What is actually quadratic programming? Because quadratic programming is the process of solving certain mathematical optimization problem involving quadratic functions. Specifically, one seeks to optimize, minimize or maximize a multivariate quadratic function subject to linear constants on the variable. And quadratic programming is the type of nonlinear programming. Programming in this context refer to the formal procedure for solving mathematical problems. Then, how to formulate the quadratic programming of n variables with m constants. Then separable programming. Separable programming is an appropriate method for solving certain nonlinear programming problems. A separable function is one which can be expressed as the sum of subfunctions where each function is a function of one variable only. The separable programming model or method is applicable if the objective function and the various constants are separable. Then the graphical methods and how to use the graphical method to solve the NLP and the steps to solve the NLP problem graphically, and one example how to solve the NLP by using graphical method. And the Contactor conditions.